Alrighty, welcome guys. So we're going to do a kind of virtual class going over the notes today because we're all, still snowed in our house. Hope you guys are safe and warm wherever you are. So remember to keep up with Google Classroom announcements and, things like that. I did have a Google Meet open today and only saw a couple of you. So remember when I post those, stop by, say hi, check in, ask questions, all that good things so that you are successful. All right, so we are going to continue our discussion about the solar system. Specifically, today we're going to be focusing on how the solar system came to be, like the formation of it, essentially. Um, there's a little bit in your online textbook. Remember, go to OpenStax, just search OpenStax Astronomy. There's also that PDF on your Google Classroom. So I like this cool picture at the beginning of chapter 7, which is where we're going to kind of focus in on. It's talking about showing a picture of all these different orbits of main things in the solar system. So you've got the sun there in the middle. You notice how they're all kind of on the same kind of flat-ish disk, like kind of almost like on the same level, so to speak. And then, of course, there's a few, random ones like Eris, one of the dwarf planets, and you've got Haumea and Makemake. They have to make things difficult. They're out really past Pluto, like kind of into the Kuiper Belt. So that's a cool diagram to show you all. I mean, notice the shape, just like we talked about, all the orbits are elliptical. So like that kind of stretched out circle, almost egg-like, stretched out egg shape, right? So we need these slides. All right. So we're gonna talk about the formation of the solar system. So how did it come to be? All that good stuff. As we're going through these, I expect you to be writing down your notes just like you would if we were in the classroom, and this was on the whiteboard or whatever. Your assignment for today is going to be not only obviously watch this video as you take your notes, but when you write down your notes in whatever your notebook or method you're using, remember handwritten ones can be used on quizzes. Um, Once you have the notes completed, take a good picture of the entirety of your notes, not just a portion of them, the entirety of your notes, and then you'll upload that to the Google Classroom. That will be your grade for the day. So really easy points here, guys. Literally just watch the video, take the notes, upload a picture, boom, 100%. So again, if you have trouble with anything or you need explanations further about something from this notes, message me, all that good stuff. All right, let's go ahead and get into this. So, formation of the solar system. All right, so this is a very quickened view, so to speak, of the formation of the solar system. So it start off kind of something like this, with essentially a whole bunch of dust and gas, and it's kind of like a cloud-ish structure. It's wasn't really organized. There wasn't a whole lot of anything precise going on. So the reason we had to start talking about gravity and its influence on other objects near it, and in terms of like if something has more mass or less mass last week, is because it plays into how the planets form specifically and why they are the way they are. So we got to talk about basically kind of the steps of the formation of the solar system and why things kind of are the way they are based on the evidence we have. Because remember, anything in science is coming from evidence. It's not coming from, well, I feel like I'm super smart today, so you should just totally believe me. That's not science. Um, Remember, we are looking at evidence. Now, in this kind of scientific endeavor, it's not like history evidence where you can have like a journal or something from somebody who was there and writing in their first person narrative, their perspective of what happened, during World War I or World War II or whatever. Um, Obviously, no humans were around when the solar system was forming. It kind of defeats the purpose. So it's not like there's a journal floating about in the galaxy, like, oh, hey, here's what happened. Um, so we are looking at like spectroscopy. So looking at different elements and the chemical signatures they give off and how much there are of them. We can look at something called radioactive carbon dating. So we can essentially look at radioactive elements, and they have half-lives that are like in the millions, if not billions of years. And so we can look at how much of those elements are around, and then in certain objects, and we can figure out the age of like the solar system and things like that. So we're looking at actual concrete number evidence, not just I think it happened because I noticed a funny cloud. I don't know. The point is we want science evidence. This thing keeps getting in the way. All right, so Supernova. We'll get more into these specifics about what how certain stars go supernova and certain ones don't in the next unit when we talk about the HR diagram and all that things that associate with it. For now, just know a supernova only happens if it's a very, very big star, hence the word supergiant. Okay. Like I'll tell you this, I'll alleviate any concerns now. Our sun is not going to ever go supernova. It is not big and spectacular. It is frankly kind of wimpy on the stellar scale. Um, the sun will eventually burn out, as in a sense, it'll run out of fuel, but it's not going to go supernova. A supernova is, yes, that large star. Again, keyword there is large or giant. It runs out of fuel. These giant, giant stars that have so much gravity because they're so massive. Well, when you run out of fuel, that gravity then causes the whole entire star to just collapse. And it's going to set off this chain reaction of explosions called a supernova. Um, Supernovas are very, very bright. There was an incident, I think in the 500s. I can't remember exactly who it was, but Tycho star. Basically, they saw the remnants of a supernova by the time that light reached us here, and it was very, very different, very clear, like it appeared suddenly because it was such a massive explosion. Now, does that mean the supernova happened the day before? No, because remember, even though light is the fastest thing in the universe, it takes a very long time for that light to reach us here on Earth from wherever it's coming from. That's why we talked about what a light year is and things like that. Okay, so when this supernova happens, star runs out of fuel, it collapses, it explodes. It sends remnants of the star, dust, gas, different types of elements, all through the area. And this is called an interstellar cloud, this whole big grouping of dust and gas. Okay. So this interstellar cloud, there is a ton of different ones out there. One is there's different types of nebulas. We'll get into those later on as well. But a nebula is essentially a large grouping of dust and gas and sometimes heavier elements that are all being held together again because gravity in a particular area. And what can happen here is that gravity eventually can then coalesce parts of it back together where new stars can form from this dust and gas and remnants and all that stuff. And that's why we call some nebulous stellar nurseries. You'll see a really cool nebula in Orion's belt, and that is also a stellar nursery, Orion's nebula, hence the name. So if you ever get to chance look through a telescope, you can see Orion's nebula in the winter, because remember it's a winter constellation in the northern hemisphere, and you can see one of those nebulas, that stellar nursery, those remnants of dust and gas and things like that. Why is it cutting off like this? I don't like that. Boo! We'll do it this way. Pause. Next. Okay, so protostar formation. So you know what a star is, essentially. It's a big ball of burning gas, right? Proto means first. So a prototype of something is like the first iteration of whatever it is, right? If somebody hands you a prototype of like a new app for the phone or a new device or something, you're probably not expecting it to work perfectly, right? Because it's the first one. So remember, proto means first. All right, so we start off, we've got a cloud of dust and gas. That gravity is starting to clump things together. When certain things start to interact and get closer and closer, we also generate heat. Okay, because there could be some friction being generated as things are circling each other very closely. We could start to have things running into each other. Heat is being generated. Heat can be given off in different forms. In this case, it's going to be giving off light. All right, so think about that. If you've ever put your hand over a light bulb, yes, it's giving off light because you can see, but you can also feel the heat with your hand because it's giving off heat. Heat is a form of energy. Light is a form of energy. They're just in the different wavelengths and frequencies, like we talked about on that electromagnetic spectrum, the EM spectrum, remember, where there's visible light and infrared and all that. Hopefully that's ringing a bell. So we're giving off a little bit of light. There's a whole lot of heat building up inside. Things are starting to kind of get closer and closer together because gravity is clumping them. And it's kind of like a domino reaction when you involve gravity to this extent and things are starting to get closer together. Well, now we're going to build a bigger and bigger mass. In this case, the clump that's called a protostar. So it's going to start to have a stronger gravitational pull and so on and so on and so on. It's kind of like that domino effect. I don't want that. I don't want that. Computer. All right, set that. All right, so phase one is the spinning. So we've got this thing called a solar nebula. Again, clump of dust, gas being held together, gravity, spinning, movement, all that good stuff. Again, it's that domino effect. Once one thing starts attracting somebody else, something or something else, it gets bigger. That's going to attract more things, going to attract more things, so on and so on. This is going to cause some of the energy to be directed, and it's going to all be directed in the same direction, same movement of direction, right? This is what's going to cause what we see today as a spinning of our solar system. So we have the protostar with the solar nebula. It's spinning. That spinning is still there today. The solar system is still moving through the galaxy. Remember that picture I showed you of the artistic interpretation of the Milky Way galaxy? Remember, we're on the Orion arm, and we are moving. So the galaxy itself is moving through the universe, okay? And then we, the solar system, are moving through around the center of the galaxy on the Orion arm. And of course, the Earth is moving around the sun. And of course, the Earth is spinning itself on its axis. There's a lot of movement going on. Okay. But obviously, we're adapted to it. We're used to it. We don't feel that spinning. So. But the reason I point this out is because, again, we are still spinning today, but this is what started it way, way back when. Okay. So once you start to spin stuff fast enough, it's going to start to flatten. Gravity is going to pull the heaviest things, the heaviest dust and gas to the center. This is going to cause things to spin even more fast. They're going to keep picking up speed. A good example of this is ice skaters. If an ice skater wants to spin in a circle very, very fast, they pull most of their mass, their center of gravity, to the middle, just like this lady's doing in the little picture here. If she has her leg out to the side like this, when she's spinning, one, there's drag, air resistance, things like that, so it's going to slow her down. But if she pulls everything in very, very closely, like if she, in this picture, she's lifting her leg up above her, which, how does she do that? Or if they just have both of the skates on the ice and they tuck their arms in and tuck their legs in and they spin really fast, what's happening is they're using angular momentum to cause that spin to go faster because they are not dragging themselves down by being more spread out. Same thing happened with the solar system. So we're starting to get stuff all clumped together. We're starting to spin. We are going to pull the heavier stuff to the middle. And as this is happening, we're spinning faster and faster, so we're starting to flatten. Okay? Because our solar system is a flat disk. Very big plane. So it's a flat disk, right? So remember we talked about the solar system. So we got the sun, got the planets and our elliptical orbits. And then, we've got the asteroid belt kind of in the middle, kind of that dividing line out here. Way at the edge is the Kuiper belt with all the icy bodies and some dwarf planets. And then we have the Oort cloud, which is kind of like the sphere that goes all the way around it. Okay. But the solar system itself is pretty much a flat disk. We're all pretty much on the same plane here. That's why we have the ecliptic. That's why we can track different constellations and the movement of the planets. We can see them at certain points. That's why the planets can look like they line up in the nighttime sky like they kind of are right now. It's because we're on basically the same plane, that ecliptic. All right, phase 3, planetesimals. So we've got a whole bunch of dust and gas coming together. Gravity is doing gravity's thing, and we're starting to form these planetesimals, which is basically like a little baby planet. It's a little baby planet, okay? And again, it's kind of like if you have a whole bunch of siblings and you've got some older ones and some younger ones, and everybody's unleashed at the dinner table at the same time. Who's going to get the most food? The bigger ones, right? The older ones. Same thing here. Okay, the ones that started to attract with their gravity and collect the most dust and gas and all that first, well, they just had to kind of edge up. They got even more dust and gas, so they became even bigger. Kind of like an unfair system almost. Okay, these smaller planetesimals started to run into each other. Remember how we talked about where we think the moon might have come from? We talked about the different theories that are for the lunar origin hypothesis, and one of them was there was an early Earth, and then there was another planet size, kind of similar sized body, maybe about the size of Mars, and they ran into each other, and pieces flew off, kind of like you see in this kind of graphic down here, and they gravity coalesced the dust and debris and all that together, and we got the moon. Kind of similar thing is happening here at the beginning of the solar system, because I just want to be very clear when all this is happening, it's not all polite. It's not like, okay, you run into you and okay, I'll collect that over there. No, it's chaos. There's explosions, there's heat, there's things running into everything. It is a lot going on. Okay. So smaller planets, or planetesimals in this case, they're running into other ones. If there's enough gravity and the collisions are just right, we're going to start to accumulate even more mass. So the planets are getting bigger. And then what we got a little bit of dust and gas remaining. And what's going to happen is that gets kind of pulled in closer to the center, closer to the sun, because it's the main point of gravity in our solar system, like we've talked about. There's a reason why we all go around the sun is because it's the biggest mass. Okay. Now, we talked a little bit about the composition of the planets and characteristics of planets. If you remember, we have the inner planets, aka the terrestrial planets. Remember, terrestrial means it's a rocky surface. We can stand on it, we can walk on it. Terrestrial from terra, meaning Earth. We kind of influence the name of the other planets that way because we like our planet. And then we have the outer planets, sometimes called the gas giants or the ice giants or the Jovian planets, all of which are acceptable answers. And they're very, very different from each other. Like there's not a surface to land on out on Jupiter, Saturn, Uranus, or Neptune. They are compressed gases, almost like a liquid stage to the point, and they're very, very like just layers and layers and layers of swirling atmosphere. But once you get through all the atmosphere, assuming you can, which you can't right now as a human or even a robot, um, you're not going to find anything to land on. There's nothing there, right? So, but we have to wonder, because there is a clear pattern here. Why did this happen? Why are they so different? And why are they kind of grouped together the way they are? Because if you remember, the terrestrial planets, Mercury, Venus, Earth, and Mars, are all grouped together. And then we have the asteroid belt. And then we have the Jovians, which are all gas, ice, giant, whatever's. And they're all very similar to each other, but they're very, very different from Earth and Mars and all those. So what happened here? So essentially, once we started having, the early planets and all that formed, so the sun makes something called solar wind. It is still a thing today. It's essentially like off-gassing from the sun. And it's basically bursts of energy. When solar wind happens today, we can track it for the most part. We know when it's coming, if things are going to be really bad. Basically, when this different things from the sun interact with our magnetosphere on Earth, we get the aurora borealis, the northern lights and the southern lights, because it's interacting and causing all those patterns to diffract and things like that. So again, that happens today. But what happened is these solar winds in the early part of the solar system, it's able to push certain elements that were in, gaseous form, like hydrogen, helium, ammonia, methane. Oh, wait, where did those sound familiar from? That's what the Jovians are made out of. Hydrogen, helium, ammonia, methane. Okay. Those solar winds push these gases out further away. And so they eventually settled further away from the sun. It wasn't enough to push them out of the solar system, right? But it pushed them out far enough. And it left the heavier elements here closer to the middle. So that's why the heavier elements like silicon and iron and all those are close to the sun because they couldn't be pushed away by the solar winds. So that's why our planets close to the sun, the inner planets, all are rocky bodies, is because they're the heavier elements. Whereas these lighter ones were pushed out there because they're just lighter weight. If you look at a periodic table, hydrogen is element 1. It's very, very lightweight. Helium is also very lightweight. It's element 2. Okay. And then ammonia and methane, those are bigger molecules because they're not just one element, they're combinations. But either way, they're light enough. They're not as heavy as iron and carbon and silicon and all that. So they got pushed out. So that's why we see these patterns in what is happening with why we have these groups of planets the way they are. Okay. So when you get back to class, I don't know what day. I don't. We'll see. I have another little slide set you'll see when I post these tomorrow. But basically, I'm going to have you go through and I have some different cards for you to fill out so you can practice putting these steps in order. So you're going to see these slides as well. If it helps you to write them in your notes as these steps, I would. So remember, step one, we start off as a nebula. We know what a nebula is, right? This is the pillars of creation. I think the Hubble took that picture, but there's been a newer version with James Webb, I believe, and it's really, really pretty. So then we have the nebula is contracting, it's getting smaller, that gravity is causing all this. Things are heating up because of the collisions. Because remember, anytime there is anything running into each other, energy is being transferred from one thing to another thing. That's just basic physics. Energy cannot be created or destroyed. It just moves from one place to the next place. And heat is a great way to move your energy. Then we're going to start to spin this cloud of stuff that's all running into each other for step 3. Step 4, everything is starting to spin. It's going to try to fling everything outward, but at the same time, gravity in the center is going to say, no, 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 stay with me. So it's kind of back and forth. That's why we are going to get a flattened shape. Okay, and then we move on to step 5. It starts to look like a disc because it's just flattening and flattening and flattening. So here's kind of a cute little cartoon. Again, the sun's in the middle, the planets are out here. And then eventually the planets are starting to form, the sun is starting to form, all that stuff is happening. Okay. The sun in the middle is forming because of a process called fusion. I don't expect you to know the difference between fusion and fission. It's has to do with molecules and movement and whether they're being broken in different bonds and things like that. Don't worry about that. But the point is, molecules are fusing together. They are getting hotter and hotter because energy is transferred, and eventually we get the sun. Yay! The sun is good. We need that. When this happens, obviously, you're very close to the sun. It's very, very hot. Even though Venus is the hottest planet, if you are on the side of Mercury that is facing the sun, it is still really toasty. It is like positive 800, 900 degrees. I can't remember the exact temperature off my head, but it is quite toasty. Okay. Let's see. So this is a good point. So if you remember in middle school science, they talked about the states of matter and what's happening with the different molecules in those states of matter. So in a gas, typically the molecules are very spread out. They're very energetic. They're moving around. They're bouncing around, doing all the things. Okay. That's why gas doesn't take a definite shape. Whereas in a solid, the molecules are very close together and they are very chill. They're still moving. They're still vibrating, but they're more chill. And a liquid's kind of in between. All right. So this is another reason the gas giants and the ice giants were pushed out. In addition to the solar winds, it's also because the closer you are to the sun, the hotter it is. Those gases don't like being super close to the sun. It just kind of, energy only reaches a certain point, but it speeds them up to a point and they can't stay there. That's they move on out. All right, step 7. Again, further you get from the sun, the cooler it is. So that is going to cause the gases and ices and all those things to stick together because they can now condense. You remember that word from talking about the states of matter? Condensation is where things all come together. Like the condensation on your water bottle on a hot day is all the water vapor molecules that were gas condensing because they came into contact with a cold bottle and then they roll down the side as a liquid. Okay. So that's how we got some of these icy bodies out way, way, way out there. Okay. And the solar system continues to cool. So this is going to allow the rocky planets, the inner planets, to start to coalesce and condense as well. But we're actually going to use a word here called accretion. Means it's kind of the same thing. We're accumulating, we're sticking stuff together. And in this case, we're looking at rocky material, we're looking at metals, because think about, all the different metals that we have here on Earth. Like those just didn't happen. And then we have step 9 again, outer solar system. It's so cold, we're so far from the sun and all that energy and the heat transfer, they're just kind of stuck there now. Everything that's stuck together during condensation is just like, well, we're here now. Cool. So that's where they are now, and that's why we have those outer planets, and that's why we call them ice giants. And of course, we have the Kuiper Belt, which is full of icy bodies, like comets and things like that, what we talked about. So this is kind of a very, very rough overview of the formation of the solar system. So when we get back into class, I will have some little cards for you to sort and put in order to help you practice the order of what's happening here. I do want you to make sure you know the steps of what is happening when. If it helps you to write out step 1, 2, 3, 4, whatever, fine, cool, you do you. But the point is, you are going to have questions on a quiz about the formation of a solar system, and I expect you to know what happened when. Okay? So keep that in mind. Remember, your task is to write down your notes, take a good picture of them, the entirety of your notes, not just like the top portion, all of it, and then upload it to the Google Classroom, and you'll be good. You'll get your 100. And it's wonderful when we all smile and have a good day. All right. If you have any questions over any of the work from this week, obviously shoot me a Google Classroom message, email, whatever, and I will see you guys very soon. Stay safe, stay warm. Let me know if you need anything, and I hope you are doing great. Bye, guys.